All right, Megan, I will say a few words of introduction here to both the audience of people joining us on Zoom and to the audience in Psych Student Union. My name is Bradley Flam. I'm the Director of the Office of Sustainability, and I'm very happy to welcome you to the second presentation in our Sustainability Research and Practice Seminar. The Office of Sustainability is very proud to co-sponsor this series, along with the Office for Research and Sponsored Programs and the Sustainability Council's Scholarly and Creative Activities Committee, of which the chair, Professor Kurt Polosinski, is here with us today. For those of you who are here in person, we have a schedule of all of the talks this semester. Fascinating talks. Please, if you are interested, come get a copy before you leave, or everyone is welcome to get a copy by going to the Office of Sustainability's homepage. And if you scroll down to the bottom, you'll find a link to a PDF copy of the schedule. Every Wednesday at this time and place, both on Zoom and in person for those who can't join us. So without further ado, I would like to introduce Professor Megan Fork and hand the digital floor to her.
Great, thank you so much. So the first thing I'm going to do is share my screen, which I can't do while talking despite the practice that I've had. So bear with me for just one moment, please. Okay, so now I hope what you see is my projected slides. Great. I also want to start off by saying thanks for bearing with me on Zoom. I know it's like we're all back in person instruction and stuff, but Wednesday is a very hectic day, and I was picturing myself running up flights of stairs out of breath after this, and I was just like, maybe this is just the way. So thanks for bearing with me. I appreciate it. So I want to talk to you today a little bit about emerging contaminants in streams and rivers. So this is I'll tell you a bit about some past work I've done and some current work that we're just getting up and running here at Westchester. I'm not going to give, I'll give a little bit of background, but this is really kind of set up as a research talk. So I don't have a ton of background about every kind of emerging contaminant, and the reason for that will become clear in just a few minutes. But before I get into that research, I want to start off, I always like to start off with acknowledging the many hands and the many minds that made all of this work possible. I want to acknowledge the co-authors that I have on some of the past work that I'll present, and the student researchers here in biology that are collaborating with me to help make some of our current work possible, as well as our funding sources. The College of Math and Science, which funded some of our current work here, and the National Science Foundation that funded some past work. So today we're talking about emerging contaminants. And so let's start off with a definition of what we mean by that term. So I think a good definition of emerging contaminants is chemical or biological materials that are not commonly monitored and that don't have clear regulation, but are known or are likely to affect ecological health. Some examples of chemicals that fall under that very broad umbrella are flame retardants, pharmaceuticals and personal care products, nanomaterials, algal toxins, like if you've heard of harmful algal blooms, the toxins produced by those bacteria and algae, industrial chemicals like PFAS, which we've heard a lot about lately, pesticides, and microplastics. So I'll just say a couple of additional things about some of these examples of chemicals. Persistent organic pollutants is another term that we'll often hear. And so those are also under this umbrella of emerging contaminants. Many pesticides fall under that category of persistent organic pollutants like DDT that we've talked about in the past, as well as PCBs and things like that. And then PFAS, which I mentioned, is sometimes called one of these forever chemicals because they they persist in the environment for a really long time. And with many of these different kinds of chemicals, they are produced for, they have a lot of valuable properties that make them present in a lot of products and manufacturing processes that we use every day. So think like PFAS are used in greaseproof paper, foam dispersant, insulation for electrical wires, Scotch Guard, defogging sprays, and things like that. So these chemicals are, you can see from this list, they have a wide range of applications. They kind of have a wide range of backgrounds, why they're manufactured, where they come from, and the chemical properties that they're bringing to the table. And what really unites this really diverse group of chemicals under this emerging contaminants umbrella is that they don't have a clear regulation. Some of the reasons why this broad class of chemicals aren't clearly regulated is in part because of the way that we regulate chemicals here in the US. So chemical regulation falls under the EPA under a couple of different acts. So one of those is the Toxic Substances Control Act, and the other is the Pollution Prevention Act. And part of the reason that we don't have clear regulation is that the development of new chemicals under this emerging contaminants umbrella can outpace the rate at which we can evaluate them for their toxicity and their impacts. So part of those EPA regulations require that we perform these pretty detailed analysis and evaluation of the impacts of these chemicals. And we simply just can't keep up those evaluations with the rate at which new chemicals are being developed and implemented. So in the case of things like flame retardants or PFAS, anytime we finish a regulation, realize that something is harmful and we should not use it anymore, there's kind of another one already waiting in the wings to swoop in and take its place. In other cases, we don't necessarily have technology or reliable and affordable ways to measure these chemicals in the environment. So if we can't routinely monitor them in the environment, it's really difficult to make regulations. So if we don't have technology that allows us to detect or to monitor these chemicals in the environment, then it makes it really difficult for us to develop regulations about how much can be there. So one of the things I mentioned was the rate of development of these chemicals. And so I'm just bringing this graph in here to kind of highlight that. So here along the x-axis, we see time from 1955 to 2015. And on the y-axis, we see a proportional change relative to the 1970, the number of these different chemicals or the development either in the US in terms of pharmaceuticals in the light pink and pesticides in the at the global scale in the darker red there. So I just want to highlight the fact that we're developing, bringing new compounds to the market all the time, and this rate has been a really steady increase over the last, what is that, like 80 years now. Yeah, so we have a lot of these. They are kind of constantly being produced, more and more of these emerging contaminants being produced and therefore added to the environment. So today I'm going to tell you two stories. As we said, this is a really broad class of chemicals, so I'm going to zero in on just two examples. I'll tell you a story about pharmaceutical contamination in streams in Baltimore, and then I'll tell you a little bit about some work that we're just getting going looking at microplastics here in Pennsylvania. So let's start off talking about pharmaceuticals in the environment. The first point I want to make is that pharmaceuticals are relatively ubiquitous in freshwater systems. We see them in broad studies that have looked at all different kinds of water bodies, such as the one I'm presenting here. We've found them, at least in some concentration, pretty much everywhere we've looked. And this includes streams in really remote national parks and things like this. So this is a study from the US Geological Survey, where they went out and sampled hundreds of water bodies and found these different counts of the number of different chemicals that they detected. And these different bars just represent different regions of the US, from the Pacific Northwest, Central, Northeast, and Southeast. I also want to make the point that why do we care about pharmaceuticals being in the environment? Well, one of the reasons is because they can disrupt physiological and ecological processes, even at low concentrations. So when we're thinking about toxicological studies, how toxic are these contaminants to animals, it usually takes relatively high concentrations to actually kill things. Like, one of the measures that we would use would be, what's the concentration at which 50% of these organisms die? And that's, I mean, yeah, that's very meaningful. Those concentrations matter, and they can be standardized among compounds. But I want to point out that even at concentrations well below those of toxicological interest, we can still see physiological and ecological processes being disrupted. And one of the reasons for that is these chemicals are designed to perform a biological function in really low concentrations, right? When we take pharmaceutical pills, it's just a small amount of that compound, but it does things to our bodies. That's by design. And so it shouldn't really come as a surprise that even at low concentrations, we see effects in the environment as well. And I want to point out that one of the best known sources of pharmaceutical pollution to the environment is treated effluent from wastewater treatment plants. And this is not a failure of our wastewater treatment plants. These facilities are just frankly not designed to remove this kind of pollution. So it's not that they're being mismanaged. It's not that they're doing anything wrong. It's that they are designed to remove a different kind of pollution. And so kind of any pharmaceutical pollution that they're removing is just a bonus to what they're designed to do. So in the study that I'll talk about today, we, using that background information, we came up with the question of, okay, so there are plenty of urban watersheds that don't receive wastewater treatment plant effluent. What that means is the sewage that's produced by the people living in that watershed is piped in sewage pipes across the watershed boundary to another wastewater treatment facility. So there are streams running through urban areas where they're not receiving any of that wastewater treatment plant effluent. So do those kinds of streams, do they also have pharmaceutical pollution? If so, how much? And what are the likely sources? So we're going to talk through the answers to all these three questions. And we answered these questions using this super awesome, unprecedented data set from Baltimore. So when I arrived to take on this project, these data had already been collected through an incredible effort of a bunch of people working at the Baltimore Ecosystem Study. This watershed that you see on the left here, this is a map of the watershed. Just to orient you, we're kind of looking at Baltimore City in the lower right. That's the tip of the Chesapeake Bay in the light blue there. And then this watershed extends from kind of dense downtown Baltimore up into the suburban and exurban areas in Baltimore County as we move to the northwest. I had to think about directions there for a minute. So within this larger watershed that drains into the Chesapeake Bay, we have a number of sub-watersheds delineated with different population densities. So up in the suburbs, the population densities are relatively low. And then as we move down toward the central city, we have higher and higher population densities, more and more urbanized landscapes. And at each of these, at the stream at each of these locations, we collected water samples for 1 year and screened those water samples, those weekly water samples for 92 different pharmaceuticals. So over the course of the year, we detected 16 different compounds that belonged to 9 different pharmaceutical classes. And I'll talk about what I mean by those classes in just a moment. But so we screened for many things and we found a relatively small subset of those compounds, but up to 16 different compounds. And I also want to point out that each of these sites where we collected our water samples, we also have measurements of stream flow at a relatively high density. So depending on which of these little yellow triangles we're looking at, we have stream flow measured every 5 or 15 minutes over the course of that whole year that we can match up to those water samples. So here's another way. I told you we found 16 different compounds from 9 different pharmaceutical classes. So here in this figure, as we look at that list on the y-axis of different colors, those are the 9 different pharmaceutical classes that I'm talking about. So these are grouped by kind of the effect that these pharmaceuticals are designed to have. So for example, we've got in blue, we see antidepressants. In pink, we see analgesics. Those are painkillers. One of the main things we see there is acetaminophen, which is the active ingredient in Tylenol. Just to point out a few, in yellow, about in the middle there, we've got the antibiotics. Now, as we go from left to right across this graph, when we look at these boxes, we have our watersheds ordered in from the least dense in terms of population density to the most dense. So we're going from the places where the houses are on big lots out in the exurban parts of Baltimore County, all the way to, on the right, the central city. And then the color of these squares is representing the percent of samples where we detected pharmaceuticals. So this is the percent of possible detections. So it's if we detected all 16 compounds on every week that we sampled, we would be at 100%. And so these are all less than that because we didn't detect everything all the time. But the pattern that I hope that you can see in this graph is that for most of the compounds, as we go from left to right, increasing population density, we tend to have a higher percentage of detections. And we also see more of those boxes that have color in them. So we're starting to see more different classes filling up our graph as we're seeing more detections and more different kinds of compounds detected as we go from left to right or increase our population density. This is a slightly different way of looking at these same data. So here I'm summarizing our data over the course of the year into a mean concentration of these different kinds of pharmaceuticals. So before we were looking at how many times did we detect them, now we're looking at what is the concentration. And here I think the pattern is even more clear, that the concentration, the total concentration, the total height of that stacked bar increases as population density increases. So the more people that are living in a watershed per unit area, the higher the concentrations of pharmaceuticals that we're seeing in this stream. And remember, this stream does not have a wastewater treatment plant in it. So despite the fact that we're not getting effluent from the wastewater treatment plant, we're still seeing plenty of pharmaceuticals, and they're increasing the more people that we have. So for the rest of this chunk of the talk, I want to focus in just on the watershed outlet. So this is that in the map, it's the one that's circled in pink there, that part of the watershed that's draining directly into the Chesapeake Bay, kind of encompassing all of the rest of the data. It's also the most dense site. So this one is the one that's right in downtown Baltimore. the one with the highest number of detections and the highest average concentration. So we're going to focus in there. The name of this site is Gwynns Falls at Carroll Park. So Gwynns Falls is the name of the stream that we're looking at, and Carroll Park is the park at which we access this site. So again, at this site, we found 16 different pharmaceuticals from 9 different classes. The most commonly detected pharmaceutical, so the one that we found the most over the course of the year, was an antibiotic called trimethoprim. And we found that in just about half of the samples. The highest concentration we ever detected was of acetaminophen, which again is the active ingredient in Tylenol, at a concentration of just less than 4,000 nanograms per liter. I recognize that this number is meaningless right now, and I'm going to give you just a bit of context in a minute. But this is kind of a coarse summary of the data. One of the most powerful things that this study let us do is look at concentrations over time, because the sort of broad scope that let us know that pharmaceuticals are in a lot of different streams, that graph, that sort of bar graph that I showed at the beginning, almost all of those studies are people going out just once to any given stream. So what we're missing by doing that is how dynamic these concentrations might be over time. And what we find is that they're actually really dynamic. So if we go out on any given day, we might be missing a lot of the picture, because the concentrations that we measure can change really dramatically from week to week. So here, this figure is showing us how these concentrations varied over the course of that year at this watershed outlet. So there's a lot of graphs here. Starting at the upper left in black, we see the total concentration. So that's all of the pharmaceuticals that we measured on any given day, their concentration added together. And then I also have it broken down by the different classes that we've been looking at. So some things to notice here are that there are some pharmaceuticals that show up fairly often, right? So if we look at the bottom left, that's where we see the antibiotics, and we see that those show up fairly frequently compared to some of the other ones. Whereas there are other pharmaceuticals that we only see maybe once or twice. So if we look at the anti-epileptics or the opioids in purple and green respectively, we can see that we only actually found those one time out of our 50 weeks of sampling. So if we had gone out on the day where we didn't detect that, we might think that that compound is not in our system. But by going out repeatedly, we can see that these patterns are that we have differences in the mixtures that these streams are exposed to. And I said I wanted to provide a little bit of context for the kinds of concentrations that we're looking at. So I want to, one thing I want to say is that nanograms per liter, which is the units that we're working here, this is a very dilute concentration. For example, I have that pink arrow there pointing at 100 nanograms per liter. That is about the concentration of a pinch of salt in an Olympic-sized swimming pool, right? So we're talking very, very dilute. So for one, it's just incredible that we have the ability to detect these concentrations. I'm kind of always amazed that we have, we have methods that can be used to detect things that are this dilute. But it also highlights the fact that we can detect ecological changes. We can detect changes in the behavior of animals like crayfish and fish living in systems with concentrations of pharmaceuticals that are this dilute. So it really underlines the fact that these compounds have biological effects even at very low, very dilute concentrations. These matter. It would be really easy to look at a concentration of the pinch of salt in an Olympic-sized swimming pool and say, oh, that's like nothing. There's hardly anything there. It can't matter. But these these pharmaceuticals have biological and ecological effects at these very low concentrations. So we wanted to start thinking about what's driving the variability in these concentrations, right? We see these kind of lack of coherent patterns, right? We're not seeing the same behavior among these different pharmaceuticals. There's no clear seasonal pattern. And there's not really any pattern with stream flow. One of the first things that we look at with kind of traditional contaminants like nutrients is this pattern between the stream flow and the pharmaceutical concentration. And that is not a relationship that we see with pharmaceuticals. We can see plenty of them at very high stream flow during storms, or at base flow when streams are just flowing along doing their thing. So let's revisit our research questions. We looked at these data from this stream, and we found that we do see pharmaceutical pollution even in the absence of this wastewater treatment plant. So we've confirmed that there's some pharmaceutical pollution in this Gwynns Falls watershed. To answer how much, we looked at concentration, but one of the things that we wanted to do was characterize the load of pharmaceuticals in this stream. So to do that, we take the concentration that we measure at any given time and we multiply it by the flow. So we have a mass per volume, that's our concentration. We have a volume per time. And when we multiply those together, what we end up with is a load, which is a mass per time. So why do we want to work in load instead of concentration? Well, load lets us ask a couple of different questions. First, if we're standing in the stream thinking about what's going on upstream, load lets us identify the different sources and pathways by which pharmaceuticals enter the stream. So if we have a mass per time, we can start to think about what % of that mass is contributed by different potential sources. So we can think about leaks or overflows in the sewage infrastructure versus what would be coming in from a wastewater treatment plant were that part of our system. Looking downstream, load is really important for thinking about the ecological risk for receiving waters. So this is why when we think about regulations for the Chesapeake Bay, for example, those are based on total maximum daily loads, because we want to know how much mass of pollutant is being delivered to the bay. So that's why we start to think about loads instead of concentrations. The concentrations matter for the critters that are living in the stream itself, but the load is what determines the impacts on the organisms living and receiving waters. So what I'll show you next is the results from doing these load calculations, multiplying those concentrations by the stream flow and aggregating that over the course of the year. So we're going to look at annual loads that are reaching the Chesapeake Bay from this watershed. So here, looking at this figure, what we're looking at here is, again, those different classes of pharmaceuticals along the y-axis. And then along the x-axis, we're looking at the total annual load in kilograms. So we used 4 different methods to estimate this. I'm not going to go into the details of all of those methods, but suffice it to say that we can look at the, oh, I can use my cursor, haha. So we can look at the sort of average of these symbols to figure out the average load based on our estimation methods. And what we see is that for most of these loads, we're looking somewhere between 0 and 2 kilograms reaching the Chesapeake Bay. And when we start to look at the analgesics, we're looking at more like 15 kilograms. So a pretty wide range of the mass of different pharmaceuticals that are reaching the bay. And if you're like me right now, you're thinking, I have no frame of reference for what 15 or 2 kilograms of a pharmaceutical is. So let's add some context. just for context, when we're thinking about analgesics, this load of 15 kilograms is the equivalent of about 30,000 tablets of Tylenol being crushed up and dissolved in the water and moving into the bay. For antibiotics, we're looking at about somewhere between about 740 to 2,400 adult doses of antibiotics. And for antidepressants, and somewhere in the range of 9,000 to 51,000 doses of antidepressants. So this is a lot of stuff. This is from a watershed with a population of about 350,000 people. If we were to aggregate that to the entire Chesapeake Bay, has this watershed represents about 2% of the total population. So when we aggregate this to the entire Chesapeake Bay, what might be coming in, this is a very small percentage of what is likely reaching the Chesapeake Bay. So we've talked a little bit about how much and the fact that these pharmaceuticals are in there. So let's talk about what are the likely sources? Where are these things coming from in the absence of wastewater treatment plants? So the tool that we'll use for this is a watershed mass balance, and I'll just talk you through. We'll build this this figure together and talk about it. So we're going to start by looking at the antibiotic trimethoprim. So again, this is the compound that we detected most frequently. It's an antibiotic that's used like mainly for urinary tract infections and things like that. And so what we did was collect a bunch of publicly available data from kind of a whole bunch of different sources. I've listed them here on the right so you can get a sense of what we did to build this data set. And then we constructed this mass balance that starts with, okay, what is the total mass in kilograms that people are using every year in this watershed? And then following that mass as it goes through different pathways to eventually get to the environment. So we'll start off looking at human use. So humans use the 350,000 people that live in this watershed altogether use about 24 kilograms of this drug trimethoprim every year. Our bodies are relatively inefficient at metabolizing this antibiotic. So what that means is most of it we excrete unchanged into our sewage. So the majority of that people are using is going into our sewage. From there, we used some information reported about the leakage rates of sewage, and we found that just about 1% of the volume of sewage leaks on its way to the wastewater treatment plant. And the majority of that sewage is actually, again, routed outside of the watershed to a wastewater treatment plant that's in an adjacent watershed. So about 1% of that sewage is leaking in place, and then most of it is being transported outside of the watershed. The stuff that's being routed to the wastewater treatment plant, the wastewater treatment plant is relatively inefficient at removing this pharmaceutical from the waste stream. Again, remember, it's not the wastewater treatment plant's job. It's not designed to do that. So it shouldn't be a surprise that it's not removing a ton of this stuff. What that means is that most of it is coming out the end of the pipe into the effluent in an adjacent stream. Whereas the stuff that's in the leaks is going into our streams, it's going through the soil or in sewage overflows and things like that, being routed into the stream. And then together, those two streams come together in the harbor, which is part of the Chesapeake Bay. So altogether, what we see is a little bit less than half of the trimethoprim that people take is what is eventually making its way into Baltimore Harbor and the Chesapeake Bay. Now we can compare that mass balance to acetaminophen, which is the active ingredient in Tylenol. So in this case, right, trimethoprim is something that we get by prescription for a relatively acute condition, whereas people take acetaminophen much more frequently. It's available over the counter. And so one of the outcomes of that is that people use much, much more. So people use about, what have we got? Like 4 orders of magnitude more, 3 orders of magnitude more acetaminophen than trimethoprim. There's much more of it being used, but our bodies are much more efficient at metabolizing this. So what that means is the vast majority of what people are using in terms of acetaminophen, we actually metabolize that. So we excrete very little of it back out into the environment. So of that 20,000 kilograms that people are using, about 1,000 of those kilograms are making their way into the sewage. And again, about 1% of that sewage is leaking. The rest of it is being routed to a wastewater treatment plant outside of the watershed. And the wastewater treatment plants are actually pretty efficient at removing this particular compound. So one of the patterns that we've seen in our data is that when the ones that our bodies are relatively efficient at removing are also the ones that are relatively efficiently removed by the wastewater treatment plants. And so what that means is that very little is actually coming out in the treatment plant effluent. So only about 3 kilograms are coming out as effluent from the wastewater treatment plant in that adjacent stream. And what that actually means is that even though leaking sewage is only about 1% of the sewage that people produce, this is actually a bigger source of the environment for acetaminophen, just because the wastewater treatment plant can really efficiently remove that. So altogether, we're getting a total load to the Baltimore Harbor that is slightly less than the one we see for trimethoprim, even though people are using so much more of this pharmaceutical. So what this difference really highlights is that the amount that makes it, the percentage that makes it to the environment really depends on the identity of any given compound. It's not a similar pattern across the board. So some of the takeaways that we're seeing from this section of the talk, leaks in aging infrastructure are contributing pharmaceuticals to streams. What that means is that our choices and our activities about the chemicals that we're using and how we maintain and upgrade our infrastructure have consequences for the streams and coasts in terms of the pollution that they're receiving. Okay, we're going to switch gears. And I want to introduce a project that we're just getting underway here in Westchester about microplastics. So we're going to talk a little bit about microplastics in streams and rivers. Starting definitionally again, microplastics are simply defined as pieces of plastic that are smaller than 5 millimeters. So that 5 millimeters is about the size of a pencil eraser. So pieces of plastic that are equal to or smaller than the size of your typical pencil eraser. And these can come in a few different types. One of the first divisions we use is thinking about primary microplastics, which are things that are manufactured to be small pieces of plastic, like beads or pellets. They used to be very common in toothpaste or face wash and things like that, but they've been really phased out over the last several years. And then secondary microplastics, which are formed by the breakdown of larger plastics like films, like grocery bags and things like that, foams, fibers, and fragments. So this is on the right here. We just have a breakdown of the relative abundance of those different types of microplastic in streams that drain into the Great Lakes. Fibers are one of the most common things that we see in freshwaters, and those are mainly derived from washing synthetic clothes. Washing synthetic clothes can break up some of the fibers that, like fleece and things, that are made of and put them into waterways. So thinking about the microplastics altogether, trash that's in the stormwater, big pieces of plastic that break down in the environment and become these smaller pieces are a major source of microplastics. Treated wastewater effluent, which is where a lot of these fibers are derived from. But we also see microplastics deposited from the atmosphere in rain and snow. Why do we care about microplastics? Well, again, like we don't fully understand all of the risks, but some of the things that we do know is that these plastics themselves can leach toxins as they sit in the water, and they can also have toxins stick to the outside of them and then re-release them when those microplastics are ingested, for example, by wildlife. Microplastics have also been shown to be growth surfaces for harmful microbes, so they can provide habitat for microbes that we might not want around. Microplastics can also interfere with animal digestion, so they can just plug those bugs and small animals up. And we still have a relatively poor understanding of the risks to human health that are posed by these particles. So we've done about I think we've done 2 field trips so far to start collecting data on this new project that we're getting underway. So I am really lucky to be able to collaborate with some awesome student researchers who have been real champs going out into the field in the 20-degree weather that we've been having, helping collect these samples. Yeah, again, starting 2 weeks ago. So some of the questions that we're trying to answer are how common are the microplastics in snow in Pennsylvania? And part of the reason that we are inspired to answer that question is that we know microplastics are detectable in the snow, even in really remote places. So I put this photo in here of folks sampling snow for microplastics up in the Siberian Arctic. But we wanted to ask, like, that's a pretty far-flung place. What in a place with more population density and things such as we're in here, how common are these microplastics in the snow? And as the snow is melting, is it releasing a pulse of these microplastics into streams that are affecting the aquatic organisms living there? So we're comparing 2 sites. We're comparing Plum Run right here in Westchester, and we're also visiting Forest Hills Run, which is up in Mount Pocono. Part of the reason for this is because back when we were planning this project, I wasn't sure it was going to snow this year. We've gotten really lucky so far. We've gotten some great snowfall that we were able to sample a couple of weeks ago. But we can also compare that to Mount Pocono, which gets about 3 times the average annual snowfall that we get here in Westchester. And so throughout the spring semester, we're going to collect snow as long as it's there. We're going to collect stream water, stream sediments, and the invertebrates that are living in that stream. And we're going to process and analyze all of those different types of samples and count the amount of microplastics that we see. So again, this is a brand new research project, so I don't have answers or data to share with you at this point, but I look forward to doing that in the future. And yeah, we're already starting to see microplastics in the snow that we're collecting. So that brings me to the end of the content I have, and I would love to have some conversation with you, talk through your questions. If we don't I do have to teach like right at 1, so if we don't have time to talk about everything, I just wanted to throw my Twitter or email up there so we can still have a chance to have a conversation, even if we run out of time right now.
Thank you very much, Professor Fork. If there are questions here, I'll have people come up to the laptop so they can pose them, but perhaps there are some from the Zoom audience first.
I'm trying to find where the chat is too. Okay, great.
Let's see, I don't see anything in the chat just yet. Are there questions here we could start with? Walt or Kurt, or?
Yeah, another question.
Could you?
Sure. Hey, Megan, it's Paul Kressler.
Hey.
Hey, I was hoping to meet you in person today, but that will be
Yeah,
another day.
sorry.
Yeah, no, it's okay. It's great to see you. So just the other day, I was got my Windex bottle out to clean the robin poop off my windshield. And I noticed it said made from 100% ocean-bound plastic. Have you seen that phrase before?
I have not seen that particular phrase. I mean, I assume they're scooping it out of, I know that we have like traps and things that we put in rivers. So I guess scooping it out before it gets to the ocean is
Well,
the
that's what it turns out
implication.
to be, 'cause I just looked it up. I was just thinking about it as you were talking about the microplastics, and I said, well, that's acknowledging a very painful thing about most plastics. It's ocean bound,
Yeah.
but actually, what it's ocean diverted plastic apparently. So it's supposedly certified to have been made from recycled plastic found 30 miles from a coastline.
Oh, wow. Okay.
So that's a program here. But anyway, what do you think of efforts like that?
Oh, okay. I mean, I think I'm gonna try to answer this in a way that's not as long-winded as I want to. But so I think it's really, I mean, it's good to clean up plastic in the ocean. And I think I think those efforts though get a lot more kind of splashy attention than efforts to keep plastic out of the environment in the first place. So, we just at the beginning of the year, now we have a single-use plastic ban in the borough of Westchester. And I think things like that are actually a much more cost-effective and much more sort of cost-effective and effective way to keep plastics out of the ocean, because it's expensive to go out there, scoop them up, clean them up, recycle them. It's much better on kind of all fronts if we can keep them from getting there in the first place. I think it's a really similar, it's very analogous to thinking about CO2 in the atmosphere, for example, right? It's like, it's very costly to go and pull CO2 out of the atmosphere as kind of this big industrial way to solve climate change. It would be much more cost effective if we could just reduce the amount that we're emitting in the first place.
I like that.
So I just
Oh,
had a
this is kind of fun. Sorry.
So you mentioned earlier that there are pharmaceutical contaminants emerging from the water treatment plants. Are you aware of any legislation or like, initiative to modify these plants in addressing this issue?
So I'm not aware of anything that's currently happening in the US, but in the European Union, some of these kind of advanced water treatment plants are starting to come online. We're still sort of in this phase of learning about it, but the EU just passed oh my gosh, I can't think of the word, like a thing where they said, oh, we're gonna work on this. It's not like a binding legislation, but it's I can't think of the word off the top of my head, but yeah, so they're thinking both about this sort of end of pipe solution of upgrading wastewater treatment plants to be better able to remove pharmaceuticals, but they're also thinking about like the upstream in the system of that. So thinking about up at that like human use end of the spectrum, thinking about like, oh, one of the things we talk about sometimes is that we can overprescribe antibiotics and things like that. So thinking about how we can be more targeted in how we're prescribing and using medications as well to sort of keep them out of the system from the beginning. Is that a good answer to your question?
Yeah, that
Great.
explains it. Thank you.
Hello. This is a two-part question. In thinking about the wildlife with the Tylenol and the antidepressants, mean, we can at least assume that they're living happier lives with less headaches. No, I'm just joking. But seriously, on a serious note, I'm curious about your research, the stream studies. Is that grant funded, or are those extensions of your classes, the Mount Pocono and the Fall Run study?
Yeah, so that particular project is funded by the College of Math and Science. So it's a RIMS grant, which is a research in math and science that is funding that. And then it allows me to pay a couple of the student workers that I'm working with and fund our travel back and forth for that project. Yeah. So yeah, I will also say about the antidepressants and their effect on fish and crayfish. So there have been studies that like monitor the behavior of these guys. And one of the things that we find, for example, crayfish exposed to antidepressants get a little bit bolder. So they, I don't know what I don't know how to say about their mood, but they are more bold when they're going for food or fighting each other. And one of the things that can do ecologically is they're more bold, they're a little bit less cautious, so they might be more likely to face predation because they're just like out there ready to fight or ready to do what they do, but are a little bit less cautious, worried about predators and stuff like that.
Hi, Kurt Kolositsky in chemistry, and the total load from Baltimore and the next, just the step down in urbanization, right? They were nearly the same load, right? But the makeup of the load was totally different, right? Acetaminophen was way off the charts for Baltimore, and it was much smaller in the next load. But the next one was more the
Yeah, I can pull that.
Do you have any idea why the mix of the two is so different?
Yeah, that's a great question. And I can tell you, like, from a data standpoint, the reason it looks like this is because we had this one like screaming high concentration that we measured. So here in the Gwynns Falls, the outlet, we measured this one screaming high concentration, whereas everything else was about an order of magnitude less. And so that really pushed that average up. When I think about the sources in these places kind of along this flow path, it gets, compared to the way that we normally think of how chemicals work in watersheds, it gets really complicated really fast, because if we're thinking about leaking sewage pipes, it really matters when someone flushed their toilet, when someone took a dose of acetaminophen, and where that person lives relative to the stream. So we did a back of the envelope calculation, thinking about the levels of detection in our methods, and we determined that we could detect if like one person took a dose of acetaminophen and then that made its way to the stream, we would detect the effect of one person taking a dose of acetaminophen. So all of that is to say is that these concentrations that we're measuring are, I think, really dynamic and reflective of things being very dynamic in the watershed. And so what that means is, like, this average concentration, when we're thinking about the furthest downstream site, is really heavily influenced by the potential effects of, like, just a few households or something like that. So it could be something like if we sampled at 11 in the morning instead of 10 in the morning, these numbers would look really different.
Or perhaps you could rephrase that as how many Ravens fans partying outdoors who didn't run back to the house, how many would it take to set a minute for display?
Yeah, there is a study from a place in southern Sweden where they measured the concentration of illicit drugs in the river that runs through the town before and after a music festival, and they found a big difference. So yeah.
Well, Professor Fork, we're almost at 1 o'clock, and we don't want you to miss your class, and we want to let folks here get to their next class or lunch
Yeah.
or whatever you're doing. So thank you very much. Please join me.
Thank you so much. It's been really fun. I would stay all day and talk more if I could, but yeah, if you want to continue this conversation, please feel free to email me or tweet me or whatever.
Great.
Thank you so much.
All right. Goodbye.
Bye. Take care. Thank you.